We are talking about Google Monarch today, which is a paper from 2010. Monarch is a time series data store. So at Google, if you want to store server-side metrics, for example, how much CPU was used, and if you want to plot that as a graph, so time is on the x-axis and CPU used on the y-axis, then Monarch can store data points here such that later on you can plot them on a graph. You might also notice that there is a spike at one point, in which case you might want to dig into this position, timestamp T1. What makes Monarch unique is the scale at which Google operates. So the amount of data that is being pushed in per second is 6 million data points. In total, it is petabytes worth of data. And since it is a time series data store which will be used to track metrics in real time, this is going to need very low latency. I'm talking about less than 100 milliseconds. There's one other major problem that Monarch solves. If a system at Google is down, the reaction time totally depends on Monarch. If Spanner goes down, Monarch doesn't go down. If Colossus goes down, Monarch still goes on. It can't have a hard dependency of any of these systems. You have extremely high availability. Let's see how Google built this system. So let's go back to 2010. You're the principal engineer at Google and you hear these complaints from engineers who say, I have a system, I'm running Google Photos and my fleet of servers pushes metrics to a system, a monitoring system. Every time there's a problem, I have to log into this system and see where things went wrong. You ask them, how did they develop this? And they say, oh, there's a common library. There's something called BorgMon, which means Borg Monitor at Google. This library is used by all systems, all of the server fleets that we have, to push metrics to the monitors. So this is like you having a very large company and you have different teams in that company. Each of those teams is deploying BorgMon individually in their own set of servers. If BorgMon goes down for them, then they have to manage it. Okay, and they also have to know some internals of BorgMon to actually be able to use it. And this is not very good. You see that multiple teams are doing the same thing, duplicate work. If you can save engineering time, you can save engineering money, okay, money for the company. So you are the principal engineer, like I said, you are going to look at this problem and say, I can solve this problem in a common way by moving away from BorgMon to Monarch. This is going to be my time series data store where various metrics will be pushed in. People don't need to worry about it much because they will have Monarch clients which will be taking data and periodically pushing to the Monarch servers. And so one decision that you make almost immediately is you have petabytes worth of data which has to be accessed at any given point in time. So this system has to be in memory. Okay, an in-memory data store having petabytes worth of data is going to be a very expensive system, but hopefully with the requirements that we have, it's going to be worth it.
Let's understand what kind of data is being stored in Monarch for observing the health of systems. One important metric is request latency. Servers emit events every time they process a request, mentioning the amount of time that this request took to complete. So that could be 10, 5, 10, 2, 6, and so on. If you plot these values in a graph, it will look something like this. Visually, you can see the anomaly. But what Monarch does is make this detection even easier. Instead of plotting request latencies, it makes a histogram of request latencies. So 0 to 10 milliseconds were taken for 8 of the requests. One request was served within 11 to 20 milliseconds. And one request took between 81 and 90 milliseconds. When you plot the histogram of this, engineers can easily tell you what are P99 latencies. And also if they detect anomalies like this, they can trace the request using examples. Monarch stores examples for every window in the histogram. So from 0 to 10, you will find one example request That is a normal processing time. From 11 to 20, you'll find another example. In our case, there is only one request which took 16 milliseconds, so that will be stored. The trace ID will be stored. And 81 to 90 has one request which engineers can use to dig deeper in the system. So this histogram explains how well requests were served within a time window. The initial graph had requests with time on the x-axis and latency on the y-axis. If you look at the time window here, the resultant frequency graph notes down this time window. And what Monarch does is for every time window, it stores a histogram which explains how well the system is doing across time. So an engineer can dig into a single time window, or they can get an aggregate across multiple histograms. One of the most impressive things about Monarch is you store billions of data points in memory. This would not be feasible unless Google applied compression algorithms. If you try to keep the raw data in memory, you will require millions of servers, which is going to be too expensive. So Google applies two techniques here. One is to share the timestamp. You see timestamp 1 here is going to be shared across all the histograms generated for different metrics. This results in 90% savings when storing timestamp values. The other benefit of this is interpolating data or doing joins across metrics is much easier now because they are broken into time windows sharing the same timestamps. So if you want to see how did request latency react to changing memory usage, doing so is easy because you have a direct mapping with timestamps. The other algorithm is differential encoding. Here you have values in each histogram. Let's say 811 for these time windows. In the next histogram, you expect that most of the values will be similar. You're probably going to get 721. So instead of storing these three big numbers, we can take the differences of the numbers and store these smaller numbers using fewer bits. This helps compress every time series for every metric by around 90%. So instead of storing exabytes of data in memory, we can do with just petabytes of data.
So this is the high-level architecture of Monarch. You have a root in blue, and this is just one root node in the world. You also have zones, so 30 or 40 zones around the world, and these are like child nodes for the root. And each of those zones has a bunch of leaf nodes. Okay, so the data points are being stored here, and the query actually comes and hits the root always. Very similar to Dremel. In fact, you'll see many components are extremely similar to Dremel. You have data which is being written to by services. So every 1 second, tell me how much CPU was consumed per server. That kind of data, those data points are being ingested into this server. This is going to buffer the data for a while, and it's also going to route it to the right zone. Okay, so this router belongs to a particular zone. The router then is able to move the data to the right leaf node. It has a mapping of key to leaf, and so data can be persisted over here. Each of these leaves is connected to Colossus, which is a distributed file store at Google. There was a Google file system earlier, GFS, which used to do this. This is used for storing logs. So you can think of each metric as a log line. In case a leaf server crashes, it can go and pick up from Colossus that data and rehydrate itself. So there is fault tolerance also over here. Whenever there is a query, it comes to the root. The root tries to find where this query belongs. So what zones are responsible for the incoming query. It then sends the query to relevant zones. The zone itself has multiple leaves. It looks at the key, the list of keys that have been asked in this query, and then it hits the right leaves. Once the leaves have a result, they propagate it upwards to the zone. The zone aggregates the result, sends it back to the root, which aggregates it again and sends it back to the client. To speed up query execution, you also have an index. So at the root level, you have one index which tells you where a query should be routed. So instead of storing that index here and managing the index here, you have it in a separate component. You also have the same concept in the zone. So where does a key belong, which leaves does it belong to, is stored in an index. This is similar to a database index.
One major optimization for making queries fast in Monarch is the idea of field hints index. This is stored in the indexer. What this does is take every key that a leaf is storing and convert it into trigrams. So that's 3 consecutive characters created by sliding a window of size 3 across the key. So a trigram for courses will look like this. Start C, start CO, COU, and so on till S $. Okay, dollar here is the ending sign. And now you take each of these trigrams and hash them. You'll get a bunch of numbers. This is like the unique fingerprint of that key. When you get a query for the key, the only leaves that you're interested in are the ones which satisfy all of these trigrams, which contain all of these. So this is very similar to the idea of a Bloom filter, where an element can exist if and only if all the indexes corresponding to those trigrams are set to value 1. If this is the case, we go to the leaf, otherwise we don't. The benefit of this is 99.5% of all leaves are ignored thanks to this field hints index, thanks to this trigram algorithm. So you have sped up your query execution by 200x at the zone level. And on top of that, the root indexer reduces fan out by 80%. So again, you have sped up your query execution by 5x. In total, queries execute 1000 times faster thanks to the indexes. This lets engineers at Google find data blazingly fast.
And the other common use case is a pre-computed cache. Very often you have periodic queries being fired on Monarch. So you want to see the overall health of a server. You say what is the maximum CPU usage in the last 1 minute. So you don't need to fire a query every time from root, reach the zone and hit the leaf for that. Maybe you can pre-compute that query and store it in a cache for a zone. In some cases, there are global queries which you want to keep pre-computed. So in that case, you will be using the pre-computed cache of the root. You can imagine them to fire a query every 10 seconds to the root node. The root node goes to the zone, gets some value from the pre-computed cache. Most of the data is right here, but in case it needs to, it will go and hit some leaves and give a response. The cache is helpful mainly for repeated queries. Any general query follows the root, zone, and leaf path. Also for fault tolerance, what Monarch does is store the data not just in 1 leaf, but in 3 leaves. So these 3 leaves are chosen for a single zone. If a zone goes out, then you may not be able to query those leaves, but that's fine. At least 1 leaf server going out is not going to stop your queries. This reduces the tail latency of most queries. Also, it provides some fault tolerance. In case the leaf server has a lot of load and you want to assign some of the shards in that leaf to some other leaf, what you can do is continue serving requests on this leaf. Meanwhile, migrate the data from Colossus to this new leaf. Once the leaf is ready, after a second or 2, you can stop answering queries from this leaf and answer queries only from this leaf. Okay, so there is a period where both leaves can respond to queries, but that helps avoid request latency. That keeps the availability of the system high. In case there's any problem while migrating data, well, that doesn't reflect on the client. There's 2 other things which increase availability of the system. One is when a root is trying to get a query from a zone. If the zone is not responding for the first 5 seconds, and let's say the request timeout in total is 10 seconds, then what the root expects is the zone to start giving partial results. So this is called a soft timeout. In case you don't give me any results in the first 5 seconds, I'll cancel the query. If you start giving me results for the first 5 seconds, then I'll wait for you to complete. I'll wait in total for 10 seconds. That's my request timeout, but my soft timeout is just 5 seconds. So in this way, I'm not depending on you too hard. I can go and hit some other zone if needed, or at least I can fail the query and tell the client that, it didn't work out. You can try again after some time. The other thing is if a zone is trying to query a leaf and the leaf is not responding, then it can start hedging its bets. Meaning if you know that both of the leaves have the data, then you send the query to the first leaf, wait for a second. If there is no response, send the query to the second leaf also. You don't wait for an entire 10 seconds before this fails and tells you I'm sorry. The zone at second number 1 or second number 2 can query the other leaf, get the response quickly. Even if you have the same repeated response here, you just ignore it. And you can send back the response within 2 seconds instead of 10. So that's it for Google Monarch. It's an in-memory time series database which stores petabytes worth of data and is able to respond to queries in tens of milliseconds. Also, it has some dependency on Colossus, on Spanner, on maglev, which is the load balancer at Google, but it doesn't have any hard dependency. in case things go wrong, this is a quote from a Google engineer, if things are literally on fire, Monarch is still running. If you have any doubts or suggestions on this video, do let me know in the comments. And if you like this kind of system design content, check out Interview Ready. I'll see you next time.